In lesson 15, we're going to look at real and complex zeros of polynomial functions. So let's start with a very heavy sounding theorem called the fundamental theorem of algebra. And the fundamental theorem of algebra goes that every polynomial function of degree 1 or more has at least one complex zero. There's at least one solution for every equation. Just a reminder on the idea of a complex. Means we could have a plus bi. So there's an I involved. There potentially could be. When we talk about the zeros of a polynomial, then the highest degree of the polynomial gives us a hint as to how many different factors there could be. So a polynomial of degree n has exactly n linear factors. This includes multiplicity. Multiplicity simply meaning that we're allowing for repeats to happen. So, if you have x minus 2 squared, that squared part tells us there's a multiplicity of 2. Okay, another conversation. Now let's look at a couple of different examples. How many zeros would each of the following equations have for us? So in the equation f of x equals x plus 5, the question is really, what degree is it? So since it's a linear or first degree, that means there is at least one zero of some type in that equation. And the second equation, f of x equals 2x squared plus 7x minus 5. Okay, looking at the highest degree, it's degree 2. So how many zeros? There could be 2 zeros. And the next one, what's the degree of that 13x to the 5th plus 7x cubed minus 2x squared minus 10? Again, look at the highest degree. And so since it's a degree 5, that means there should be 5 zeros for our function. And then the very last one, x squared equals 0. Since it's degree 2, that means there should be 2 zeros of some type. And again, they might be repeated, so they might have a multiplicity on there. So now that we can identify how many potential zeros, how many zeros there are in a function, we can talk about a sort of a factored form. And a polynomial that has a degree of anything bigger than or equal to 1 can always be expressed as the product of n number of linear factors. In other words, it's always possible to write a polynomial in its factored form, and sort of you have this general case of we could have some constant, but x minus one of our factors times x minus another factor. So all of these we can sort of write out in factored form there. So we'll kind of give an example of this. Here we've got x squared minus 25. That's a difference of 2 squares. So x minus 5 and x plus 5 would be our linear factors of that polynomial. If over here we have x squared plus 2, x squared plus 4, so I can solve for 0 for a second. Now it's not factorable, but if I bring the 4 over, right, what can we do? We can take the square root of both sides, gives us plus or minus. And what's the square root of negative 4? That's 2i. Okay, so I can rewrite this then in terms of a set of factors that have complex roots. So I can rewrite it as x minus 2i and x plus 2i. But again, the point being that I can rewrite any polynomial in terms of a set of linear factors, and I can essentially write it out in its factored form for any type of factors that I want. Okay, so notice in that last case, the x minus 2i, the x plus 2i, we're not used to seeing that. This is probably one of the first times in your life you've actually seen a factored form with complex roots. And that's now an option for us in this course, is that complex numbers can come up. All right, which then brings up that if I have a polynomial function with integer coefficients, and I do have a complex root, then I also have its conjugate also has to be a root. So if a polynomial happens to have a complex root of some type, a plus bi, then its conjugate, then a minus bi would also be a root of that same polynomial. Right? We have complex conjugate roots. They come in pairs. Okay. So down here under our examples, you can kind of see an illustration of this, not just with the complex, but even with the irrational roots. So here our task is to find these zeros. What are the solutions for this particular equation? And so you can write it out one by one and just say, well, x plus 3 equals 0, so that means x is negative 3. 2x minus 1 equals 0, so bring the 1, divide the 2, so I get positive a half. But hopefully we've gotten to the point where if we have it in factored form, then we can quickly solve for x. So given this factored form, the other zeros for this function would be negative square root 2, positive square root 2. Notice we're just changing the signs of the after x. So if it says x plus square root 2, then that's a negative square root 2. X minus square root 2, it's a positive. So what about x minus 4 plus 5i? That means positive 4 minus 5i is a 0. And positive 4 plus 5i is a 0. So in factored form, those would be the zeros of this particular polynomial. Okay, so with a little bit of understanding then of the nature of roots and how degree tells us the number of zeros in a function, we can actually write a polynomial function in factored form given some information. So let's say, for example, I give you that a polynomial is of degree 3. That means there are 3 factors that I can find for factored form. They told me that one of my zeros was 1. So that means x minus 1 is a factor. They told me that 5i is one of them, so that means x minus 5i is a factor. And now we sort of have this question mark. What about the other one? They only gave us 2 zeros, so what about the third one? Okay, well, that's where the complex conjugate rule comes in. If a complex number is a solution to a polynomial, then its conjugate is also a solution of the polynomial. So if x minus 5i shows up as a factor, then x plus 5i would also show up as a factor. Okay. Down below, polynomial in factored form of degree 6. Okay, so degree 6 means I've got 6 factors that I need to find. So 1, 2, 3, 4, 5, and 6. Okay, so I have, let's see, the first 0 they tell me is negative 2. So that would be x plus 2 in factored form. They tell me x negative a half is a solution, so x plus a half in factored form. They told me that 3 plus 2i is a solution, so when I bring that over, I get x minus 3 minus 2i. And so let's kind of think for a second. If that complex number is a solution, then its conjugate should also be a solution. And its conjugate would look like 3 minus 2i. So in the parentheses then, I would have x minus 3 plus 2i. And then same thing with irrational numbers. They also have partners that show up, they're conjugates. So let's put this in factored form. So that would be x minus 4 plus the square root of 5. And so what would be the remaining factor that would have to show up? And that would be x minus 4 minus the square root 5. So the conjugate of the original after we've gone ahead and changed the signs. Okay, so in this next question, I'm going to change the verbiage just a little bit. Well, I'm sorry, I'm not changing anything that's on the paper. It's already there. But notice how the question changed for us. Do you see anything different about this question, say, than versus the last question? Do you catch the expression about the phrase factored form versus not there, right? What is that actually telling us to do? Well, that just means we're going to practice doing some multiplying and some combining like terms. So the first task is to write it into factored form, and then we'll come back and do some simplifying. So our polynomial of degree 3, so I know I can plan ahead, has got x and x and x. Okay, so what are the factors? I have x, well, the 3 becomes a minus 3, and the 2 plus I becomes a minus 2 minus I. And of course, what's missing? What's missing is the conjugate. So minus 2 plus I would be the other factor that's not there. Okay, so this I'm going to call complex factored form. It's when we have it written in its set of linear factors, but we have complex roots that are there. Okay, so now what I'm going to do is I'm going to multiply those two complex expressions together. The x minus 3 is still there, but I'm just going to multiply the x minus 2 minus I times the x minus 2 plus I together. And I'm going to be very organized when I do this to sort of keep track of all these like terms, so you'll kind of see what I mean here in a second. So x times x times negative 2, and x times I. So x times x, I get x squared minus 2x plus ix. Okay, then I'm going to come in with the second term, so the negative 2 times x, the negative 2 times negative 2, and the negative 2 times I. And negative 2 times negative 2 is 4, so I'm going to write that here at the end because I don't have a like term yet. I'm sorry, I missed the negative 2x. Negative 2x does have a like term. Negative 2 times negative 2 is positive 4, so we'll put that at the end. And negative 2 times ix is minus 2I. And again, I don't have a like term there, so I'll just kind of put that at the end. And then we have one more set of multiplies, and then we can combine this together. So we have negative I times x, negative I times negative 2, and negative I times I. All right, so negative I times x is negative ix. Negative I times negative 2 is positive 2I. And negative I times negative I is negative I squared. Okay, so let's kind of collect up all of our terms. I have x squared minus 4x. Notice the ix's cancel out. Plus 4, and then the minus I and the positive 2I cancel out, and then a minus I squared. Okay, so before we get too excited about that, think back to what I squared means. Okay, remember I squared, I being the square root of negative 1, so I squared is just negative 1. Okay, so this little piece that we wrote, that minus I squared, that's just actually negative 1. So this is x squared minus 4x plus 4 minus a negative 1. And so I can combine the 4 and the negative 1 together, so we get x squared minus 4x plus 5. Okay, now what does this have to do with anything? Well, remember all we did was multiply that x minus 2 minus I and that x minus 2 plus I. So that's going to bring us up to a different form of this polynomial. Okay, so p of x then, we have an x minus 3 and that green thing that we just simplified, so x squared minus 4x plus 5. Okay, and I'm going to give that a name. I'm going to call that factored form. Okay, so notice we don't have i's anymore in our factors. We have gotten rid of the complex nature of this, but it is still considered factored form. Okay, now what was our goal? Our goal was to find a polynomial. So guess what? We're not done yet. We still need to multiply these two expressions together. And that's okay. Sometimes math just takes takes a while to get there. It's like in English, you got to write a 10-page paper. You can't shortcut that. Not if you want to pass. All right, so I want to multiply x minus 3 and x squared minus 4x plus 5. And I'm going to do the same sort of organization I did previously. It'll be a little easier for us. So we have x times x squared, which is x cubed, x times minus 4x, which is minus 4x squared, and x times 5, which is 5x. Then I want to do the same thing with that negative 3. So negative 3 times x squared is negative 3x squared. Negative 3 times the negative 4x is positive 12x. And negative 3 times 5 is negative 15. Okay, but because of how I multiplied it and how I lined up my like terms, I can see very quickly which ones are like terms or not. So that brings us finally to our polynomial, which is x cubed minus 7x squared plus 17x minus 15. Okay, so that is our polynomial given those initial solutions, those initial zeros. So please be careful, especially on a test. And I do understand that this is a time-consuming process, and that's okay. We can handle time-consuming, right? So just be careful when it says write it in factored form versus write it in polynomial form. You don't want to just stop when you're supposed to write it in polynomial. In the same sense, you don't want to have to multiply to get the polynomial when it's all it asking is factoring. So I've seen both mistakes whenever I've tested on this particular concept.